Combination sum. Have you ever hit a roadblock in interviews with problems like combination sum? This is one of the most common Pattern Mastery 100 LeetCode questions, frequently popping up in Google, Facebook, and Amazon interviews. Did you know over 40% of candidates stumble here, not because the algorithm is hard, but because backtracking can be intimidating at first glance? Today, we're going to master combination sum step by step, so you can ace this must-know coding pattern and never freeze up again. Let's break down combination sum. We're given an array of unique positive integers called candidates and a target number. Our goal? Find all unique combinations where the numbers sum up to the target. Each number in candidate test can be chosen unlimited times, and combinations must not be duplicated or rearranged. We need to return a list of all possible combinations, with each combination as a list. What are the challenges? A brute force approach would be to try every subset, but that's exponential time, way too slow. We need a smart strategy. This is a textbook backtracking problem. We'll build combinations incrementally, backtracking whenever we overshoot the target. Space complexity can grow quickly with all those combinations, so be mindful of input size. Duplicates are avoided naturally if we always build from the current index forward. Here's our plan. Sort the candidates, optional, but helps with optimization. Use a recursive helper function to build combinations. Track the current combination, sum, and position. If the sum matches the target, save the current combination. If the sum exceeds the target, backtrack. Otherwise, recursively try adding each candidate, starting from current index. This way, we explore all valid paths without repeating or rearranging numbers. Solution 1. Backtracking, on middle.2n. We begin by defining a class named solution. This keeps our method neatly organized. This function, combination sum, finds all unique combinations of numbers from the list candidates that add up exactly to target. We're allowed to reuse the same number multiple times. We initialize res, the list that will store all valid combinations we discover. We define our helper function DFS, short for depth first search. It tries out choices step by step and backtracks when a path doesn't work. Its parameters: I current index in candidates. Cur the current combination we're building. Total the running sum of numbers in cur. We check whether our running total matches the target exactly. If so, we've found a valid combination. We add a copy of the current combination to res. This is one successful answer. Then we return because there's no need to explore further from here. Adding more numbers would exceed the target. If the total has already gone over the target or we've run out of numbers to try, there's no valid combination down this path. So we stop exploring this branch and backtrack. This is the choose step. We choose the number at index I and include it in our combination. Because we can reuse the same number multiple times, we call DFS again on the same index I, adding that candidate to the total. This is the skip step. We skip the current candidate entirely and move on to the next index. This explores combinations that do not include candidates I. We start our depth first search from index 0, with an empty combination, and a total of 0. Finally, we return the list of all valid combinations discovered. Final wrap-up. And that's how this algorithm works. It first sets up a recursive DFS function, then explores all possible include/skip decisions for each number, collecting combinations that reach the exact target. Efficient, simple, and elegant. Test case check, combination sum using backtracking. Let's test our function using this input. Candidates equals 2, 3, 6, 7, and target equals 7. These numbers represent the values we're allowed to use. Each can be chosen multiple times, and the target is the total sum we want to reach. Here's why the solution works. The backtracking function DFS tries to build combinations step by step. At each step, we can either include the current candidate again, stay at the same index, or skip it and move on to the next candidate. We keep track of the current combination, cur, and its total sum, total. If total becomes exactly equal to target, we record that combination. If total goes over the target, or we run out of candidates, we stop exploring that path. And that's exactly what our program outputs: 2, 2, 3, 7. This confirms that our backtracking logic is correctly exploring all valid paths and collecting every combination that reaches the target. Wrap up. So, our implementation is correct. The algorithm successfully finds all unique combinations that sum to the target using backtracking, efficient, accurate, and reliable. Solution 2. Bottom-up dynamic programming, ON target C. Time complexity, ON target C. We start by defining a class called solution, which keeps our dynamic programming method nicely organized. This defines our function combination sum. which will now solve the problem using a bottom-up DP approach instead of backtracking. We sort the list of candidate numbers. This isn't required for correctness, but it helps generate combinations in a consistent, ascending order. We create a list called DP, where each index t will store all combinations that sum up to t. So, DP0 will store combinations that sum to 0. DP target will eventually hold the final answer. This makes the DP table size target plus 1, giving us part of the ON target C complexity. We initialize DP0 with a single empty combination. Why? Because there is exactly one way to make a sum of 0, by choosing nothing. This is our DP base case. We iterate through each candidate number C. This loop runs n times, where n is the number of candidates. For each candidate, we iterate through all target sums from C to target. This ensures that when we try to build a sum T, we only use combinations that can legally include C. This loop contributes the target factor to our time complexity. We now look at every combination that sums to T, C. Because if we know how to form T, C, we can form T by adding C. The number of combinations stored here is the C factor mentioned in the time complexity. For each combination that sums to T, C, we add C to that combination and store it in DPT, meaning we have found a valid way to make sum T. This gradually builds all combinations bottom up. Finally, we return the list of all combinations that sum exactly to target. That list is stored in DP target, after the DP table is fully filled. Final wrap-up. And that's how this algorithm works. It first builds a DP table where each entry collects combinations for a specific sum, then constructs larger sums by extending previously computed combinations. Efficient, simple, and elegant. Test case check. Combination sum using bottom-up dynamic programming. Let's test our function using this input. Candidates equals 2, 3, 5, and target equals 8. These numbers represent the values we're allowed to pick from. Each candidate can be used multiple times, and the target is the total sum we want our combinations to reach. Here's why the solution works. We build a DP table DP where DPT stores all combinations of candidates that sum up to T. We start with DP0 equals, meaning there's exactly one way to make sum 0, by choosing nothing. For each candidate C, we iterate through all target sums T from C up to 8. For every combination already in DPT-C, we create a new combination by appending C and store it in DPT. And that's exactly what our program outputs: 2, 2, 2, 2, 2, 3, 3, 3, 5. This confirms that our DP table is building combinations correctly and capturing every valid way to reach the target. Wrap up. So, our implementation is correct. The algorithm successfully finds all unique combinations that sum to the target using bottom-up dynamic programming, efficient, accurate, and reliable. Recap script, combination sum. Let's do a recap. Ever felt stuck on backtracking problems like combination sum? You're not alone. This one trips up tons of candidates because it looks more complex than it really is. But once you understand the pattern behind it, you'll see it's just structured exploration. And suddenly, backtracking becomes your best friend in interviews. Breakdown recap. We started by defining the goal. Find all unique combinations of numbers that add up exactly to a target. Each number can be used multiple times, and order doesn't matter, only the sum does. It's a search problem wrapped in logic and structure. Assess recap. We compared brute force to backtracking. Brute force tries every subset, chaotic and slow. Backtracking, however, builds combinations piece by piece and abandons paths that overshoot the target. It's efficient because it prunes impossible options early, focusing only on meaningful candidates. Structure recap. The plan was clear. Start from the smallest combination, add numbers one at a time, and backtrack whenever the total exceeds the target. When the total hits the target exactly, record the combination. This recursive structure ensures every valid path is explored, no duplicates, no missed possibilities. Implement recap. We implemented this plan cleanly using recursion and ran it on LeetCode. The code executed smoothly, no errors, and efficiently generated all unique combinations that sum to the target. Check recap. After testing, we confirmed that the solution returned all valid results and passed every LeetCode test case successfully. It performed exactly as expected, even on trickier inputs. Closing insight. The key takeaway? Backtracking is just organized trial and error. Once you master how to control and prune your search space, problems like combination sum, and many others, become clear, logical, and even fun to solve.